In this lesson, we're going to develop an exponential equation to model exponential growth and exponential decay, but first we're going to solve exponential equations by creating like bases. These are all examples of exponential equations, so when your unknown variable is in the exponent, it is known as an exponential equation. And we can solve these equations by expressing both sides as powers of the same base. So let's look at our first example. We have 2 to the power of x is equal to 64. Can we rewrite 64 so it has the same base as over here, the same base of 2? Now you won't be expected to just come up with that in your head, so you may need to do a bit of playing around in the calculator. So once you do that, you should find that 64 is equal to 2 to the power of 6. And now we can make a conclusion here. Since we do have the same base, that means x, our exponent, should be equal to 6. Therefore, x is equal to 6. In the next one, we have 2 to the power of x plus 4 is equal to 32. So let's look at this 32. Can we rewrite 32 with a base of 2? 32 is the same thing as 2 to the power of 5. Therefore, if our bases are the same, that means the exponents are the same. So x plus 4 is equal to 5. So then we can find x by solving this little equation. So x is equal to 1. Feel free to try the next one on your own and come back to the video when you're ready to check your answer. So once we rewrote 81 as a base of 9, you get 9 to the power of 2. So that means that our exponents, x minus 3, is equal to 2. And using that equation to solve for x is equal to 5. In the next one, we have 5 to the power of x is equal to 1 over 25. So let's start off with changing this denominator into a base of 5. So that means 5 to the power of x is equal to 1 over 5 to the power of 2. Now we can't do the same thing we did in the other questions just yet. Because this 5 to the power of 2 is in the denominator, we need to take it out of the denominator. And the only way to do that right now is taking this exponent and making it negative. So that means we have 5 to the power of x is equal to 5 to the power of negative 2. These two things here are equivalent. And that means since we have the same base of 5, our exponents are equal, so x is equal to negative 2. In the next one, we have 3 times 2 to the power of x is equal to 12. Now remember, we're just trying to solve this equation and find the value of x. But we can't do anything with this 2 to the power of x yet because we're multiplying this side by 3. So to get rid of that, we need to divide both sides by 3. When we divide by both sides by 3, we can cross out that 3, so we're going to be left with 2 to the power of x is equal to 4. And now we want to make sure both sides have a base of 2, so this is the same thing as 2 to the power of x equals to 2 to the power of 2. Since our bases are the same, that means that x is just equal to 2. And here's our next question, so why don't you pause the video, try this one on your own, and come back to the video when you're ready to check your answer. So in this question, we have 3 to the power of x multiplied by 10, and we need to first undo this multiplication of 10 by dividing both sides of our equation by 10. And once we do that, we get 3 to the power of x is equal to 27. And if we take 27, rewrite that with a base of 3, we get 3 to the power of 3. Since we now have the same base, that means that our exponents are equal, so x is equal to 3. Now that we've learned how to solve exponential equations, we're going to learn how to model exponential growth and decay using exponential equations. So this is the model we're going to use, the equation that we're going to use. A represents the original amount before there's any growth or decay. B, our base, is the growth or decay factor. It represents how much it's growing by or how much this is going to decay by. And we'll look at that in more detail when we go through some examples. And the exponent x is the amount of time that it takes for growth or decay. When b is greater than 1, that means we have an exponential growth. So our function increases as our x values increase. So let's work on our first example of exponential growth. A population of a colony of cells is growing so that it will double every hour. If the colony starts off with 10 cells, what will the population of the colony be after 8 hours? We need to come up with an exponential function to model the exponential growth in this example. So let's actually make a table to help us. Our independent variable is going to be the time, and this is in hours. And the population is our dependent variable. We know from the problem that it starts off with 10 cells. So at 0 hours, that means we're going to have 10 cells. And the question also tells us that the colony of cells is growing so that it will double every hour. So that means in our table, in hour 1, we would take our 10 cells and multiply by 2 because these are going to double and we're going to get 20. And in hour 2, since every hour the cells will double, instead of 20, it's going to be 40. And we're going to rewrite that another way, incorporating what we have in the beginning. So we would have our 10, and we would multiply it by 2 because it's being doubled, but then we would multiply it by 2 again because we're doubling it again. So when we're multiplying by 2 again, we can just say 2 squared. And for the third hour, we already know that 40 is going to be doubled, and that's going to get 80. But how would we do that if we were to use a formula or use what we started with in the beginning? Well, we would take our 10, multiply that by 2, multiply by 2 for a second time, and then for a third time. So that's just 2 to the power of 3. And you can see that we've actually come up with a formula here to model this. So we've started with 10 and we've multiplied by 2 because we wanted to double this population. And in each hour it's being doubled again, so we're multiplying by 2 again and multiplying by 2 again. But instead of writing that multiplication of 2, we can use our exponents. And if we compare our time and our population, at the third hour our exponent is 3. At the second hour, we have an exponent of 2 on our 2. At our first hour, we do have an exponent of 1 here. And at hour 0, well, if we wrote this 2 multiplied by 2 to the power of 0, well, anything to the power of 0 is just 1. So this is just 10 times 1, which is just 10. So we can use this to model this situation. So we need to come up with an equation. Since we're finding the population, we can use population to represent P. We just need to make sure we state that. So P represents the population of cells. And P is equal to 10. So that's the amount we're starting with. 2 is the amount it's increasing by, and this would be our base. Looking at our table, our exponents represent the time, the number of hours. So we can use the letter n to be our exponent, and n is the number of hours. And now that we have come up with this equation, we don't need to continue this table until we hit 8 hours. We're just going to use our equation. So we're finding out what the population is at 8 hours. So that means n is equal to 8. And then we can just plug that into our equation. And when we plug that into our equation, we'll get that P is equal to 2,560. So we need to include a final statement. So there will be 2,560 cells in 8 hours. And we're done. Here's our next example. A bank pays interest at a rate of 1.2% per annum. Per annum means per year. So what is the balance after 3 years on a deposit of $1,000 if interest is compounded annually? So what does this mean? Compounded annually. And it means when your interest is added onto your account. So this means it's added once a year. So let's just make a table of values to get our information sorted out. So our independent variable is time, and it's in years. And our dependent variable is going to be the total amount you have in the bank account. So it's your bank balance. We'll only need 3 or 4 points so we can see the pattern. And once you do more practice, you should get to a point where you don't even need to make a table of values. You can go straight into creating your equation. So at the beginning, at 0 years, we have $1,000 because that's how much is deposited into the account. And we know that the interest rate is 1.2% per annum. It's added once a year. So before we find 1.2% of this $1,000, we need to turn that 1.2% into a decimal. And to do that, we can just divide by 100. So that's just 0.012. So in year 1, we're going to take that $1,000, and if we multiply by 0.012, what would we get? Well, we would get $12. But this column doesn't represent the interest, because if we multiply by just 0.012, you will get the interest, 1.2% of our $1,000. But this represents the total amount that you have in your account, your total balance. So we need to change something here. If we take our first 0 and we change that into a 1, and we multiply it by 1.012, we're multiplying by the 100% of 1,000 plus this 1.2% of the 1,000. So that means this is going to change our amount from $12 to $1,012. And for our second year, if we went back and took this $1,012, multiplied it by 1.012, you would get $1,024.14. So that's just our original $1,000 multiplied by 1.012 and then multiplied by 0 or 1.012 again. And by now you may have figured out the pattern, but if you haven't, you can continue on with the table. So we have our A value, our starting amount, which is $1,000, and we have our growth factor, our base, and that's 1.012, and we know our exponent represents the number of years. So let's write out our equation. So I'm going to use t to represent the total amount, and we need to define our variables. So t equals the total amount. You could have used another variable like b for balance, or a, capital A, for the amount. So our total amount is equal to 1,000, that's our starting amount, multiplied by 1.012 to the power of n, and we need to define what n is. N represents the number of years. And we're just being asked to find out the balance after 3 years. So that means in this equation, we need to put n equal to 3. So when we plug that into the calculator, we're going to get that t, our total amount, is equal to $1,036.43. Next, we're going to look at some models of exponential decay, and this is when our function is decreasing as our x values are increasing. and our base here is going to be in between 0 and 1. So let's go through this example. Each year, a car depreciates to 70% of its value from the previous year. If a car was bought new for $10,000, find its value after 5 years. So let's just make a table of values to help us out here. We can start off with our independent variable time, which will be measured in years, and our dependent variable will be the value of the car. This is in dollars. So at year 0, the car was bought for $10,000, so that's the value of the car. That's the original value of the car. And it depreciates to 70% of the previous year. So in year 1, the value of the car will be 70% of this $10,000. So to find that, we would take $10,000 and multiply it by 0.7. That's the 70%. And that's just equal to $7,000. And in year 2, we're looking for 70% of this $7,000. And if you calculate that, that's going to be $4,900. Or we can rewrite that as 10,000 multiplied by 0.7 to the power of 2. So we can use this to write out our equation. So we can let V represent the value, and this is equal to 10,000, that's our starting cost, multiplied by 0.7 to the power of n, and n represents the number of years. So we're looking for the value of the car after 5 years. So that means we need to substitute n with 5. And when we put that into the calculator, we get that the value of the car after 5 years is equal to $1,680.70. So here's our last example. A ball is dropped from a height of 2.5 meters and allowed to bounce freely. The height of the ball decreases by 20% after each bounce. What is the height of the ball after 6 bounces? So go ahead and pause the video and solve this problem on your own. You can come back to the video when you're ready to check your answer. Here is my solution. So I started off by making a table of values. Our independent variable is the number of bounces. The dependent variable is the height. So at 0 bounces, when the ball is dropped, it's at a height of 2.5 meters. And we know from the question that the height of the ball decreases by 20% after each bounce. So we're not multiplying by 20%. We're going to take that 20% from our 100% of the height. So the new height would be 80% of the original. So we're multiplying that 2.5 by 0.8. That's 80%. So when we do that after the first bounce, we get 2 meters. And if we do that again, we get 1.6 meters, and if we multiply by 0.8 again, we get 1.28. So this is the equation that we're working with. Our original height is 2.5 meters, and the height is decreasing by 0.8 each time. And our exponent here is going to represent the number of bounces. So our general equation is h, which represents the height, is equal to 2.5 times 0.8 to the power of n, and represents the number of bounces. And make sure you always introduce what new variables represent. So since the question asks what is the height of the ball after 6 bounces, n equals 6, so we can substitute that into our equation, and when we do that, we get that the height of the ball is approximately 0.66 meters after 6 bounces.